Welcome all in this lecture of statistical mechanics. This lecture is a continuation of my earlier lecture regarding the study of ideal Fermi system. In the previous lectures, we discussed the mathematical methods of studying the Fermi-Dirac system, and we also have derived the behavior of different thermodynamical parameters. So in this present lecture, I will discuss about the study of electron gas in metals with the help of Fermi-Dirac statistics. So in this regard, it can be mentioned that historically the electron theory of metals was developed by Drude and Lorentz. We all know about that, and we have studied the Drude-Lorentz theory in our solid state physics. So this Drude-Lorentz theory was developed by the application of Maxwell and Boltzmann statistics. So they have applied the Maxwell and Boltzmann statistics to the electron gas and derived theoretical results for the various properties of metals. The Drude-Lorentz model did provide a reasonable theoretical basis for a partial understanding of the physical behavior of metals. However, it encountered a number of serious problems of a qualitative as well as quantitative nature. So there were some problems. So what were the problems? For instance, the observed specific heat of metals appeared to be almost completely accountable by the lattice vibrations alone, and practically no contribution seemed to be coming from the electron gas. So as per the Drude-Lorentz theory, there should be no contribution from the electron gas, and the specific heat of metal arises only from the lattice vibration. The theory, however, demanded that on the basis of the equipartition theorem, each electron in the gas should possess a mean thermal energy 3 by 2 kT and hence make a contribution of 3 by 2 K to the specific heat of the metal. So as per theory, the electron gas should contribute to the specific heat. So there is a deviation from the theory or from the Drude-Lorentz theory and the theory which we have studied in Fermi-Dirac statistics. Similarly, one expected the electron gas to exhibit the phenomena of paramagnetism arising from the intrinsic magnetic moment mu b of the electrons. According to the classical theory, the value of the paramagnetic susceptibility is chi para is equal to mu 0 n mu square by 3 kT. That means the paramagnetic susceptibility depends on the temperature. But the point is that the susceptibility of a normal non-ferromagnetic metal was not only independent of temperature but had a magnitude which at room temperatures was hardly 1% of the expected value. So the first thing is that it was observed experimentally, that is, the paramagnetic susceptibility was independent of temperature at the room temperature region, and the value of the susceptibility is not matching with the theoretical prediction by the classical results. So there is some deviation in the experimental results. The Drude-Lorentz theory was also applied to study transport properties of metal such as the thermal conductivity K and the electrical conductivity sigma. While the results for the individual conductivities were not very encouraging, their ratio did conform to the empirical law of Weidmann and Franz as formulated by Lorentz, namely that the quantity K by sigma T was a constant. So as per the Drude-Lorentz theory, K by sigma T was a constant, and this particular theorem is known as the Weidmann-Franz law. But the point is that the theoretical value of this quantity K by sigma T, which is also known as the Lorentz number, turned out to be 3 into K by E square is equal to 2.48 into 10 to the power minus 13 ESU per degree square. The corresponding experimental values for most alkali and alkaline earth metals were, however, found to be scattered around a mean value of 2.72 into 10 to the power minus 13. So the point is that there is deviation from the experimental results and the theoretical prediction regarding the Lorentz number or regarding the Weidmann-Franch law. A still more uncomfortable feature of the classical theory was the uncertainty in assigning an appropriate value to the mean free path of the electrons in a given metal and in ascribing to it an appropriate temperature dependence. So all these are the failures of the Drude-Lorentz theory. The most significant change introduced by Sommerfeld was the replacement of Maxwell-Boltzmann statistics by Fermi-Dirac statistics for describing the electron gas in a metal. With this single stroke of genius, he was able to set most of the things right. To see how it worked, let us first estimate the Fermi energy epsilon f of the electron gas in a typical metal. So we know the expression of the Fermi energy. This is the expression of the Fermi energy which we have studied in our earlier lecture. Here we have replaced the value of G by 2 and we have written m prime in place of m. Why we are writing m prime? M prime is the effective mass of an electron in the gas. But why the question of effective mass in the gas? To justify the assumption that the conduction electrons in a metal may be treated as free electrons, it is necessary to ascribe to them an effective mass m prime not equal to m, where m is the electron mass. This is an indirect way of accounting for the fact that the electrons in a metal are not really free. The ratio m prime by m accordingly depends on the structural details of the metal and therefore varies from metal to metal. In sodium, m prime by m is almost equal to 0.98. So the point is that when you are considering the electron gas, then you have to consider the effective mass of the electron, and this effective mass varies from metal to metal. In case of sodium, you can consider m prime by m, that is equal to 0.98. So in this formula we will use the effective mass rather than the electron mass. Now the electron density n by v, for a cubic lattice we can write it n by v is equal to Ne into Na by A cube. What is Ne? Ne is the number of conduction electrons per atom. Number of conduction electrons per atom. Na is the number of atoms per unit cell, and A is the lattice constant. Now how we are using this formula? Another way of expressing the electron density, that is, it can be shown that the electron density n by v can be written as F into rho divided by capital M. What is F? F is the valency of the metal, rho is its mass density, and M is the mass of an atom. So what is rho by M? Rho by M being the number density of the atoms. Rho by M is the number density of the atom, that means Na, and F is the valency of the metals. So we can say F as Ne, that is the number of conduction electrons per atom. So F has been replaced by Ne, and the rho by M, the term rho by M, that means the number density of the atoms, that we are writing as Na, that is the number of atoms per unit cell, divided by A cube, where A is the lattice constant. So this is the formula of N by V, that means the electron density. Now for sodium, Na is equal to 1, Na is equal to 2, the value of A is 4.29 angstrom, and M prime is equal to 0.98 Me, and putting all the values in equation 1, we can obtain the Fermi energy of sodium, which is almost 3.14 electron volt. Now the Fermi temperature of the gas Tf, which is equal to epsilon F by K divided by K. Now Fermi temperature of the sodium will be value of the epsilon F, which we have calculated in this particular equation, that is 3.14 electron volt. That should be multiplied with 1 by K, where K is the Boltzmann constant. Now you see, in this particular equation we have written Boltzmann constant in electron volt unit. So the value of 1 by K will be this one. in electron volt unit. So that is why the value of the Fermi temperature Tf is equal to 3.64 into 10 to the power 4 Kelvin, which is considerably larger than the room temperature. If you consider the room temperature almost 3 into 10 to the power 2 Kelvin, but this is in the order of 10 to the power 4 Kelvin. So the ratio T by Tf being of the order of 1%. So T by Tf is of the order of 10 to the power minus 2. That is why the conduction electrons in sodium constitute a highly degenerate Fermi system. As per our previous discussion, we have already studied the thermodynamic behavior of the Fermi gas, and we have also demonstrated in the earlier lecture, that is, what do you mean by degenerate Fermi gas and non-degenerate Fermi gas. There we have learned that if the value of T by Tf is very low, then you can consider the electron gas as highly degenerate. So this particular case is the highly degenerate Fermi system. This statement in fact applies to all metal, that is, this is not only valid for sodium, but this particular case, that is the highly degenerate Fermi system, this fact applies to all metals because their Fermi temperature are generally of the order of 10 to the power 4 to 10 to the power 5 Kelvin. Now, the very fact that the electron gas in metals is a highly degenerate Fermi system is sufficient to explain away some of the basic difficulties of the Drude-Lorentz theory. For instance, the specific heat of this gas would no longer be given by the classical formula. So, in our earlier lectures, we have deduced the expression of the specific heat when we will consider the gas as highly degenerate. We have already deduced the expression of the specific heat. So this is the expression of the specific heat, and this expression is different from the classical expression of the specific heat, that is Cv is equal to 3 by 2 Nk. But you see that the new result is much smaller in value. Not only the expression is different, but this particular expression shows that the value of the specific heat will be much smaller than its classical values. At ordinary temperatures, the ratio Kt by epsilon m, that is equal to T by Tf, is equal to of the order of 10 to the power minus 2. So this particular value is of the order of 10 to the power minus 2. So it is quite easy to understand the value of the specific heat will be lower than the classical values. It is then hardly surprising that at ordinary temperatures the specific heat of metals is almost completely determined by the vibrational modes of the lattice, and very little contribution comes from the conduction electrons. So at room temperature, the little contribution comes from the conduction electrons, and most of the contribution comes from the vibrational modes of the lattice. So from this particular expression, we can predict that. Of course, as temperature decreases, the specific heat due to lattice vibrations also decreases, because we know that if you lower the temperature, then vibrations will also be decreased. That is why the contribution of the specific heat from the lattice vibration will be decreased and finally becomes considerably smaller than the classical value. So ultimately we will observe that the value of the specific heat is considerably lower than the classical value 3 by 2 Nk, because there is lowering of the lattice vibration. A stage comes when the two contribution, that means the contribution of specific heat from the electrons and the contribution of the specific heat from the lattice vibration, that becomes comparable in value. Ultimately, at very low temperatures, the specific heat due to lattice vibrations, which is being proportional to T cube. We know from the device T cube law that the specific heat due to lattice vibration is proportional to T cube. But if the temperature is lower, then what will happen? The vibrations will also be lowered, and in that case, what will happen? The contribution of the specific heat for the lattice vibration will be even smaller than the electronic specific heat, which is proportional to T to the power 1 from this formula. In general, we may write for the low temperature specific heat of the metal, that is Cv is equal to gamma T plus delta into T cube. So I can again describe this particular dependence of the specific heat on temperature through the graph which we have already demonstrated in our earlier lecture. So let me show you the graph again, that is the behavior of the specific heat with respect to temperature. You see the graph, that is if you consider the temperature very high, so in this particular region you see that the specific heat is independent of the temperature. You see that specific heat is independent of the temperature, and that is equal to the classical value, that is Cv by Nk is equal to 1.5. But you see that is deviation from the classical value starts almost from here. You see there is deviation of the behavior of the specific heat from its classical behavior, and this deviation goes on, and ultimately you see if you consider the temperature very low, suppose in this particular portion if you consider the variation of specific heat in very low temperature, then you see that the variation of specific heat with respect to temperature is almost linear. If you consider this particular zone, you see the dotted curve. So this dotted curve depicts, that is from starting from T is equal to 0 Kelvin to up to this point, up to this particular point, the variation of the specific heat with respect to temperature is almost linear, that is Cv is proportional to T. That means Cv is proportional to T to the power 1. That means in this particular region only electronic specific heat is countable. That means only there is electronic contribution in the specific heat. But starting from this particular portion, the contribution of lattice vibration comes into play, and it increases with increase of temperature, because you know if you increase the temperature, then contribution of lattice vibration will also be increased. So in this particular region basically there is a contribution of both electronics, contribution of both the electrons as well as the lattice vibration. So starting from this particular zone to almost this particular portion, there is contribution of electrons as well as the contribution of the lattice vibration. But if you consider that is very high temperature, then the specific heat approaches its classical value and it is almost independent of the temperature. So this is the behavior of the specific heat with respect to temperature, and what we have shown that depending upon the temperature there will be some electronic contribution and the contribution of the lattice vibration, and the variation of the specific heat we can describe in this manner, that is gamma T. So this particular portion will is the electronic contribution, and delta T cube, this particular contribution is from the lattice vibration. So gamma and delta, they are two constant. The values of gamma that can be estimated from this equation. You see Cv is equal to some constant into T, that constant is the gamma, and the constant delta you can estimate from the device T cube law. And experimentally it has been found that this theoretical prediction is quite well explain the experimental behavior. For example, one experiment was performed by Korak et al., who worked with copper, silver and gold in the temperature range 1 to 5 Kelvin. That means they have studied the low temperature behavior of the specific heat for these metals. Their results for copper are shown in figure 8.4. So this is the experimental results. In the x-axis it is T square and the y-axis it is Cv by T. That means same equation it has been plotted, that is Cv by T with respect to T square, and you see this dotted this scattered data is the experimental data, and the solid line is the theoretical prediction. So the theoretical prediction matches quite well with the experimental results. So in this lecture what we have discussed, that is we have discussed that is how specific heat depends on the temperature when the contribution of the electronic specific heat is countable. So this particular expression demonstrates that the specific heat depends on two factors. The first factor is the electronic specific heat, that is gamma T, and the second factor is the specific heat due to the lattice vibration. And when the temperature is very high, then the specific heat is almost independent of the temperature and Cv approaches to the classical value. This particular content of the lecture has been taken from the book of Patria, and I will request the viewers to study this book for further understanding, and I also thank you for listening my lecture.